Quantum computers are going to break Bitcoin. You've probably heard that before, but how real is the threat and when might it actually happen? In this video, I'm going to break down what quantum computing is, why it's often misunderstood, the specific threat it poses to Bitcoin's cryptography, and how soon it could be powerful enough to actually break Bitcoin. So quantum computers are computers that operate on the principles of quantum mechanics. Quantum mechanics states that the properties of particles, for example spin, are described as existing in a superposition of states. In other words, there is no fixed state until measured, at which point a definite state is observed. Classical computers use transistors that can be in one of two states, 0 or 1. These are controlled via logic gates. However, quantum computers are based on qubits, quantum bits, which can exist in a superposition. In other words, a linear combination of 0 and 1. The probability that a qubit will collapse to either 0 or 1 once measured is related to the amplitude for that particular quantum state. Thus, the workings of a quantum computer involve manipulating these amplitudes through quantum gates. Now, quantum computers don't work by processing multiple solutions at the same time and then automatically outputting the correct answer. A lot of people think this is how they work, but that's not really true. Instead, quantum algorithms are designed to manipulate the amplitudes of various possible states through interference, enhancing the probability of correct solutions and canceling out incorrect ones. This process increases the likelihood that when you measure the system, you get a useful answer. Today's largest quantum computer from IBM has 1,000 qubits, but the number of amplitudes grows by 2 to the n, where n is the number of qubits. Thus, there are 2 to the 1,000 amplitudes, you can think of these as parameters, to manipulate. That's more than the number of atoms in the observable universe. Okay, so we can think about the power of a quantum computer growing as the number of qubits increases. But there are other factors to consider as well, such as error correction. So for example, these qubits can be noisy in that they can inadvertently interact with their environment and collapse to a certain state, in which case the superposition is lost, which isn't very helpful. But there are these things called quantum error correcting codes, which essentially are ways of correcting for these errors. So the power of a quantum computer really depends on these two factors. One is the number of qubits, and the other one is the error rate. So if quantum computers have this potential to break modern cryptography, how would they do it, and how powerful would they need to be in order to succeed? So the way that they would do it is by employing something called Shor's algorithm, which is a mathematical algorithm designed in the 1990s to run on quantum computers, and it's an algorithm for factoring extremely large numbers. Many modern encryption methods rely on the computational complexity of large number factorization. So the next question is, if our current most powerful quantum computer has 1,000 qubits, how many qubits would a quantum computer need to efficiently employ Shor's algorithm to crack modern cryptography? Okay, so to answer this question, I started by doing a bit of research. I came across a really good article here on a website called quantumcomputingforbusiness.com. There's a lot of useful information here about quantum computing in general, but they have a section here called How Many Qubits Are Needed? And they go through sort of some recent estimates about how many qubits you would need to efficiently employ Shor's algorithm. And they cite here a recent estimate that finds that a plausible number of quantum computer would require roughly 20 million reasonably good physical qubits. So what they mean by that is 20 million qubits with a relatively low rate of error in order to factor a 2,000-digit number. Okay, so obviously this is referring to cracking RSA 2048 encryption. So Bitcoin utilizes ECDSA encryption. I'm not an expert on cryptography. I don't know enough about these different methods to say whether they are sort of equivalent. For example, if a quantum computer can break RSA, can it also break ECDSA? I don't know. But for the purpose of this video, I'm just going to assume that that is true. Oh yeah, so I wanted to quickly clear up one point of possible confusion when people hear that quantum computers might break Bitcoin. sometimes they think about Bitcoin mining. And Bitcoin mining is obviously just the process of, running to SHA-256 and running this hashing function and trying to find a hash that satisfies various constraints. It's important to note that SHA-256 is actually quantum resistant, so it's possible that quantum computers could speed up this process of hashing using something called Grover's algorithm. But it's unlikely they can use this to like break the blockchain or anything like that. It might just be that in 20 years, 30 years, everyone is running quantum hashes instead of ASICs. But, it might not be the case either because, ASICs are extremely good at what they do, and they're probably a lot cheaper to produce and to acquire than quantum computers. So yeah, where quantum computers really threaten Bitcoin is in the ECDSA signature scheme, which is used for like when you generate a Bitcoin address, you have a public key and a private key. So it's that is under threat, possibly. So let's go ahead and work with this number of 20 million qubits. And remember, today the most powerful quantum computer has 1,000 qubits. Okay, so what we want to do is try to predict when we might hit this 20 million mark. So what I did is I did a bit more research about the timelines in quantum computing, and I try to see like what is the progression like? Is this technology increasing exponentially? How are things going? So I found this article here on Wikipedia. It's a pretty good article. It's a timeline of quantum computing, and it goes through quantum computing, right from when it was first conceptualized, all the way through till today. And what I did is I just picked out the different quantum computers that have been released over time with the number of qubits that they had. And I simply just plotted that on a chart and then used that to kind of see what the trend was. So here is what that looks like. So here you can see this is the data on the left. In 2016, we had a machine from IBM which had 5 qubits. 2017, just a year later, IBM came out with a 50 qubit model. 1 year later, they had a 72 qubit machine. And then in 2019, Rigetti released a 128 qubit quantum computer. And then in 2023, which is the most recent one, IBM released their quantum computer. So what I did was I just plotted all this data on a chart, and then I fit a trend line to the data. And as you can see, this is a perfect exponential curve. So this confirms our suspicions that quantum computing is increasing at an exponential rate. But then I realized I actually missed a data point here. Supposedly there was a quantum computer already in 1997, which had 2 qubits. So I just included that on the chart, and I ran the analysis again, and you get a very similar exponential pattern, but it's slightly shallower. Okay, so the next step would be to project this into the future and see when we might hit that 20 million mark. So that's what I did over here. Essentially, I took the equation for this exponential curve and I just extrapolated it to find where we might hit the 20 million mark. So if you look on the chart here, this is the 20 million qubit mark. And if we just follow that line over, we can see that that is going to happen at about 2041. So in about 17 years from now. And then I did the same thing for the second model, and that one's not progressing quite as quickly. This one is giving a date of like, what is this, 2043 or so. So that's quite interesting. I was quite surprised. I figured it would take a lot longer for this to happen. But yeah, within 20 years, it seems like this is a real possibility. Okay, but obviously this is kind of some back of the napkin math. This is nothing out of this world. So I wanted to see kind of what are the experts saying about this? Have there been any published studies that have looked at this, and are their estimates sort of in line with mine? So let's go to this sheet. Yeah, so the interesting thing is, indeed, they are sort of similar to what I found. So here is a model on the left from that same article that I referenced in the beginning. And this is looking at different rates of development in quantum computers. And they've got kind of like bull case, base case, and a bear case, if you will. The first one assumes qubits will double every 9 months. The kind of base case is that qubits will double every year. So they're kind of relating this to Moore's law, which is quite interesting approach. And yeah, if we look at the 20 million qubit mark, which is this top green line here, you can see the base case is sort of crossing that mark actually before the year 2040. So that's like 2039 or so. So it's happening a little bit sooner than what we predicted. If you look at their kind of bear case, that will happen a lot later, maybe in the 2050 or 2060. So yeah, that's really interesting. Another thing they did was surveyed a bunch of quantum computing experts and asked them when they thought quantum computers might be powerful enough to break cryptography. And here are the results. It's a little bit confusing to read this chart, but essentially, the tipping point is really 15 to 20 years, most experts are predicting. And then, there's a fairly good consensus that within 30 years, this will be the case. So that's pretty interesting. And then finally, I found another study. This was published by Christopher Tam in 2023. Really nice study. They looked at the progression in qubits for quantum computers, and they created a model, a machine learning model, which was based on the relation to classical transistors. So a slightly different approach. And they end up with this polynomial fit. Essentially, I've just drawn a line here on the chart at the 20 million qubit mark. And if we follow that down, it's going to happen in about, 2050, 2051, something like that. So this model is predicting probably like 10 years after what we're predicting with our kind of rough model in the beginning, but still really interesting and still within that 30-year period. So within 3 decades, it seems like pretty likely to happen based on all of this research. Okay, thanks for watching. I hope this was interesting. It was actually really fun for me to go and do this research and analysis. As always, there's a link to the Google Sheet in the video description. You can check it out for yourself, make a copy, mess around with the data if you want to. I've also put links there to the various resources that I used. And I guess the last thing I'd like to say on this is that there's no real consensus around when quantum computers are going to be at a certain level or when they're going to be powerful enough to do certain things. It seems like they are progressing exponentially, kind of similar to what we see with classical computers when it comes to Moore's law, for example, which says that, transistor density increases, doubles every 2 years, and kind of has been following that pattern ever since, the 1960s, which is quite amazing. There doesn't seem to be any reason to think that quantum computers won't follow a similar exponential pattern. But like I said, some experts think that it might be very difficult to create a quantum computer with 20 million qubits, for example. Whereas some experts think that it will happen, and it could happen relatively soon. From what I've seen, I think it should absolutely be taken seriously. I think we should already have people in Bitcoin. If there aren't people already, we should have people in Bitcoin looking at this and trying to come up with proposals for instituting, quantum safe cryptography. But yeah, that's just my take. So hopefully you enjoyed this video. I'll see you in the next one.